All right, welcome back. So, this lesson we are going to talk about soil formation. So, when we talk about soil formation, we got to talk about soil properties. We have the physical properties of soil, which is going to be the layering of it, the color of it, and the texture of it. So, for the layers, we call it horizonation. And then for color, we just call it soil color. We have a reference chart that we just take like samples of soil to and reference it to other different colors that we see typically in soil. And then we have soil texture, and that's determined by the proportion of mineral separates. So basically, that's just like how much open space there is in the soil, like the pore space that we kind of talked about in rock formation. So as I move my head around here, this is the horizonation. So at the top, we've got zero horizon or O horizon. It's this is just the top of the soil. It's loose and partly decayed organic matter. That's just like the stuff that's falling off of trees and the dead plant matter and the poop that animals let loose. Then we've got the A horizon. That's going to be that humic layer mostly. It's going to be the A horizon and the O horizon where you see that humic layer. And that's just the organic layer. That's where things are living, microbes are doing their thing, they're decomposing stuff, they're adding carbon to the soil, they're doing all sorts of good stuff. Then we've got the E horizon. This is going to be when you get some like leaching going on. So like the carbon is kind of settling down and it's going down and water is going down. The B horizon, that's basically like clay and it's basically clay. And it could be like shale, things like that. And shale's just really, really like cemented clay, basically. And that gets transported from above. So it just falls down, it gets pressurized, and the more pressurization happens, the more cementation happens, the more compaction happens, and you're going to get that clay like substance. And then we've got the C horizon. That's partially altered parent material. So this is the stuff that started up here that got pushed down over a long period of time. And then this is unweathered parent material. So, this is stuff that like at a certain point was bedrock and then was either pushed up or pushed down and then layered on top of. So really, horizonation, you just got to look at the layers of the soil. If you find microbes in it, that's A or O horizon. And then anything else below that, you can kind of figure out on your own. It's not super important that you know, but that's just the basics of it. And then we've got color. So what we do is right here, we take a piece of soil and then we put it against this little color grid. And so whatever it looks like, so it looks like it's in between this one and this one. So when we see that, then we can go, okay, well, what other soils are in this certain reference chart from 3 to 3, basically, on the color chart? Okay? So they look at that, they look at a list of soils that are in that color chart, and then they'll be able to use other samples with this soil sample to kind of figure out exactly what it is. So, science is a lot of getting your hands dirty type of stuff. It's a lot of information in science isn't just given to you. You have to go out there, pick the soil up, and then look at it against other soils. So that's the cool part about science is it's not all just nerds and lab coats. I did a lot of stuff like that back in the day. So let's talk about soil structure. So that was those soil peds, or like basically how much air is in between each piece of soil. So we see a repeating pattern of soil peds, and peds are just discrete soil structural units. So it's just like little teeny pieces of soil that have air pockets in between each one. So when you see peds, think about that. It's just like basically little teeny pieces of soil mixed with air and other little pieces of soil. So the structure is going to be described by the ped size and shape. We talked about this in the rock unit a little bit, how we have siltstone, we have sandstone, we have clay, which is shale. So we have all these different things that are described with pore space and soil, and that's going to be that ped structure. So to describe like how much water basically is held inside of the peds, we use this thing called bulk density. And so that's the proportion of weight that soil holds to volume. And volume is basically just like if you've got like a water container in here, how much can go inside of this space? So what they'll do is they'll just take They'll take a bunch of soil, they'll put it in a container like this, and however much can fill up this amount is going to be its volume. Wherever, like, if they take I don't know, a gallon of soil, they put it in there, they smash it down. That's going to be the volume, and then they'll use that against weight to find density. And density is just weight over volume, W over V. And so really all that's going to tell you is like how dense something is going to tell you how much space is within it. So if it's less dense, that means there's more pore space, which means that you're going to have more ability for water to infiltrate that area. So like sand is going to be less dense than clay. And clay can hold in a lot of water because it's a lot less, or it's a lot more dense, so there's a lot less spaces. So that soil is going to hold it rather than let it fall through. So that's the main difference there. Then we've got soil consistency. And so that's just like how easily those PEDs that we talked about are deformed by fingers. And so that's also water content is very important for that one as well. So if you can like grab something and move it around and kind of destroy it in your fingers, like sand, if you take a bunch of sand and you move it around in your fingers, you're going to get a bunch of individual grains. Nothing's going to kind of like stick together. Whereas with clay, which holds in a lot of water, you're going to put that in your finger, you're going to move it around. It's going to be the same ball of clay, basically. So it's got a really good consistency. And so that's how we kind of determine the physical properties of soil, is like how much water it can hold, how easily that's deformed by our fingers, which is also has to do with how much water is held, and then just like how dense it is. So that's also has to do with how much water it can hold versus how much water is let through those pore spaces like sand. So here we've just got all sorts of different PED sizes and shapes. So this is like a really, really consistent clay. Like this looks like if you get it and you put some water in it and you do this to it, it's going to stay pretty much the same shape. But this stuff right here, it's got a whole bunch of loose PEDs. So if you grab this with your fingers and do this to it, this is what you're going to get. It's a whole bunch of other little teeny pieces of that particulate. So that's going to be the consistency right here, consistency. So this has like less consistent soil because you can break it apart. And then also it's got a lot of pore space. So this is going to allow a lot of water to flow through it. So this is going to be less dense than this because this has more weight by volume than this does. So it weighs less. If they're the same size, like if they're both this size, this one on the right weighs more than this one on the left. Okay, so we've talked about physical properties. Now we've got to talk about chemical properties. And so we talk about soil reaction, or pH, and that's just percent hydrogen. It's the percent log hydrogen. It's a really complex term, but really all pH is the acidity versus alkalinity of something. So that's acid versus base. So if you are low on the pH scale, which goes to 14, if it's a 0 to 6 on the pH scale, then that's going to be more acid. And if it's 7, 7's neutral. If it's over 7 to 14, then that's going to be basic. So you think of like chalk and stuff. A 1 would be like lemon, and then a 14 would be like chalk. So imagine eating both of those things and how they taste, and that's pretty much the same thing with most acids and bases. So the acidity or the alkalinity, which is basicness, of a soil is very important to it. And it's affected by the climate, the parent material underneath, and vegetation on top. So sometimes vegetation dies and then it falls down, it permeates. Permeates means like it goes through holes, essentially. And so it permeates through these layers of soil, and then it mixes with water and it creates a acidic solution called carbonic acid. And so that will do a lot of things to the underlying bedrock. If it's like limestone, we'll get that chemical weathering going on, and we'll get like karst topography happening, which basically karst topography is like sinkholes. And that's due to carbonic acid permeating through the soil layer and then sitting on bedrock, and then it sits on that bedrock for a long time and it weathers away, and then you get a hole. And then that's when houses fall through the ground. So soil reaction, or pH, impacts plant and microorganism growth. So with a lot of acidity, you're going to get less organisms. So in like wetlands or bogs, like especially Ireland, they have a lot of peat there. And peat can only form, it's basically coal, it's like less compacted coal, that can only form in an acidic environment. And that's because there's less microbes to destroy all of that or convert all of that dead plant material into its own energy. So when it does that, it just kind of turns it into gas. When those microbes are gone, then that turns into some sort of organic, like compacted material that you can burn and use for fuel. So they use a lot of peat in Ireland for fuel, P-E-A-T. It's kind of like coal, but it's less compacted. So then we have this thing called the cation exchange capacity, and that's just the soil's ability to replace metals in the soil and use those metals. So metals exist as cations in the soil, and cations are just like anything, basically anything that's like positively charged. So when it's in that soil, the roots actually replace these metal cations with their own cations. And so it says right here, subject to replacement by other cations. So they replace those metals in the soil and use those as nutrients, like iron and nickel and all sorts of things like that. They're important for retaining and supplying nutrients, and they also help to absorb contaminants. So if you've got a lot of heavy metals coming down some runoff, if you have plants that their roots are pretty highly negatively charged, then they can suck up those highly positively charged heavy metals coming through and kind of like cleans up the area. And so that's what wetlands are really good for, is they have really good cation exchange capacity, and they are very great for kind of stopping pollution in that area, or at least making it smaller. So then here we go, how soil pH affects viability of plant nutrients. So really all this is this is the scale. This is acidic down here. This is basic. So molybdenum, this is something that we mine here in Colorado. Same with copper and zinc. So in the soil, for them to be available for nutrients to plants, the molybdenum is very highly alkaline. So you're going to have kind of an alkaline environment in the soil if you find a lot of molybdenum, and then you're going to find that those plants are probably sucking up a lot of molybdenum, and it's a very alkaline environment there. Whereas iron is very acidic. So you have Fe, which is iron, in your blood, and your blood is acidic. So this is the same thing here. If you find a lot of iron in the soil, you're going to have an acidic solution in the soil. And not that that's a horrible thing, but it just affects the availability of plant nutrients. So here's that cation exchange capacity. Really, here it is right here. The roots, the exudates with H ions. Essentially, it loses hydrogen ions, and it gains all of these positively charged metal ions. So like iron, calcium, salt, that's sodium, magnesium, sodium again. All these things, they kind of swap them out. So this one, it loses its hydrogen ions, puts it into the soil, makes it more acidic, and then this way it takes in the manganese or magnesium, takes in those cations and puts them back into the roots and uses them for growth. So plants are actually pretty smart and very capable. So when we talk about healthy soil, what are we talking about? We're talking about mostly humus and soil tilth, but it really depends on the size of the rock particles, the oxygen content, the moisture content, the hydrogen content for the acidity versus alkalinity. And then in minerals and rock particles, they supply plants with their basic nutrients to grow. So shortage of nutrients inhibits plant growth. So all these little metals, these are really important for those plants to grow. So that's why they continuously are sucking them in and getting rid of hydrogen. So here is a good picture of healthy soil. We've got microbes in here. We've got plants working along here. It's got good pore space. Water can go down, but it also gets stuck so that plant can continue to use it. It's also going to create sort of an acidic environment with the microbes, which is going to break down those metals and make it so that they're soluble in water so that the plants can suck them back up. So what do microorganisms do? They're critical to soil health. They carry out decomposition, which releases nutrients into plants, but the main thing is they release carbon dioxide, which creates an acidic environment when mixed with water, and that will dissolve those rock particles, like those metals, so that the plants have a steady flow of nutrients.